In today's lesson, we're going to try the you try examples in our notes on graphing rational functions. We're starting with example number 4 in those notes where we're going to go ahead and see if we can factor. Looking at the numerator here, I have a -5 up top that I want to multiply to, and I want to find factors that add to -4. So my two factors are -5 and 1. Because my a value in front of my x squared is 1, I can go ahead and factor the shortcut method, writing those factors next to x in my parentheses. In the denominator, I'll also see if I can factor. I have -2 that I want to multiply to, and -1 I want to add to. The factors that multiply to -2 and add to -1 are -2 and 1. And again, because I have a coefficient of 1 in front of my x squared, I can just factor my shortcut method of x minus 2 and x plus 1. As I see, I have two factors on top of each other that will cancel out here to simplify my function down now to cleaning it up with just x minus 5 in the numerator and x minus 2 in the denominator. Remember, whatever you cancel is going to become the x value of your whole. You just have to do the opposite. So instead of +1, we have -1 as the x value of our whole. To find the y value of your whole, remember that you have to take this x value and plug it into your simplified function. That's going to give us -1 minus 5 over -1 minus 2. That simplifies down to -6 over -3, which comes out to be a +2. That's the whole I'm going to go ahead and plot on my graph. For the vertical asymptote, remember that's always setting the denominator equal to 0 every single time, every single case. So that's exactly what we're going to do. The denominator is x minus 2 equals 0 in the simplified version. I have to solve that out by adding 2 to each side, giving me my final answer of my vertical asymptote when x is 2. So when x is 2 on my graph, I will go ahead and draw a dotted vertical line as my vertical asymptote of this graph. Next, I have my horizontal asymptote, and I'm scrolling back to the cases now of which case we have here. As a reminder, case number 1 is if the degree is less than the denominator in the numerator. And then case number 3 is if the degree is greater in the numerator than the denominator, which we did not have here. We had the degrees being equal, so that's case number 2. If the degrees are the same, we play the coefficient game. So I'll go ahead and have my horizontal asymptote be the degree of my numerator, the leading coefficient, over the leading coefficient with the same degree in the denominator. So as you see in my simplified example, we have a case number 2, and that will be 1 over 1, which 1 divided by 1 equals 1. That's going to be my horizontal asymptote in this case. You see the x squared terms in the numerator and the denominator. That's my highest degree exponent. And I divide the coefficients on those. Make sure you draw that horizontal asymptote dotted line on your graph to add that in. For the x-intercept, we're always going to set the numerator equal to 0. And that's going to be x minus 5 equals 0 in this case, because that's the numerator of my simplified function up top. I have to solve that equation down to one step, so I'll go ahead and add 5 to each side to get my x-intercept occurring at 5, 0. I go ahead and plot that point on my graph on the x-axis at 5. For my y-intercept now, that's going to be replacing my x value, specifically with the number 0 every single time to find the y-intercept. I'll give myself some room here to be able to solve this out. Yeah, I'm fixing my arrow here because it wasn't the best. So f of 0 equals, instead of x minus 5, a 0 minus 5, over, instead of x minus 2, a 0 minus 2. I solved down the numerator to one number to get negative 5, and I solved down the denominator to one number to get negative 2. This is when I then am able to simplify and cancel out two negatives, making a positive 5 over 2. That gives me 5 over 2 as my y-intercept. Thinking about that as a decimal, that's about 2.5 or 2.5. So that's exactly where I'll put my y-intercept point. Next, we go ahead and state that we have no slant asymptote because we do not have the case of the degree of the numerator being 1 degree larger than the denominator. They're the same degree, so there's going to be no slant asymptote. For domain, we're always going to have x cannot be equal to the x value of the whole if we have one, which we do. So that's where I'm getting this value of negative 1 because that's the x value of our whole, which means I cannot include it in our domain, as well as the vertical asymptote's x value equaling 2 can never be included in the domain as well, and that's always where I'll get my numbers from. For the range, it's the same idea, except for we have to have y cannot equal the y value of the whole, so that's going to be 2, where I'm getting that from. If you look back in our information, that's the y value of our whole. And it also cannot be the horizontal asymptote, which has a y value of 1. Okay, we go ahead and find some more points by plotting it into our function here. So when I find more points, I'm looking to the left and right of my dotted vertical asymptote. I have a value, a whole, at negative 1. I have a y-intercept at 0, but I don't know what's happening at x being 1, so I'm going to solve that out. Looking kind of the 3 points or 3 x values to the right of my dotted vertical line, I know 2 is the vertical asymptote, the vertical dotted line, but I don't know what's happening at 3 and 4, so I'll put those in my table. But I do know what's happening when x is 5, that's my x-intercept. So I'll plug in 1, 3, and 4 just to get a few more points on each side of my graph. And I'm going to erase those numbers just so that way when I'm graphing, we're not graphing over those. Okay, let's go ahead and solve these. So into this simplified function, I now have 1 minus 5 instead of x minus 5, and 1 minus 2 instead of x minus 2. I solved that down to get a negative 4 on top with a negative 1 on the bottom, giving me 4 when my x value is 1. Plotting that point helps me get my line that's going so close but never passing that horizontal and vertical asymptotes here. Kind of like my boomerang right there. Go ahead and plug in 3 as well. Instead of x minus 5, I have 3 minus 5. Instead of x minus 2, I have 3 minus 2. 3 minus 5 is negative 2. 3 minus 2 is 1. And that comes out to division of negative 2 when my x value is 3. That's my point. When I plug in 4, I get 4 minus 5 now, and 4 minus 2 in my denominator, simplifying to negative 1 up top and 2 on the bottom. So when my x value is 4, my y value is negative 1/2. I plot it halfway in between my 0 and negative 1. I go ahead and graph at the last point here, it getting so close but never touching the horizontal asymptote. I connect all the points I have, and at the last point, I get so close but never pass the vertical asymptote. And that's my two boomerangs for my rational function here, and let's try the U-try number 5. My first step is always seeing if I can simplify or factor the function. I can do nothing with the denominator because the x minus 2 cannot be factored anymore. Up top, I can't do the big X, but what I can do is see what I can take out of each term, which is a 2. GCFing out a 2 leaves me with x plus 2 left inside. Nothing cancels, but I still have a simplified fraction. Since nothing cancels, I have no hole in my graph. Holes only occur when you have a common factor up top and in the bottom that cancel, that we remove because it's a removable discontinuity. For the vertical asymptote, remember that's always and forever setting your denominator equal to 0. So when I set this denominator equal to 0, I go ahead and have x minus 2 equals 0. I solve that one-step equation by adding 2 to each side, getting me my vertical asymptote at x equals 2. That's where my vertical dotted line will go. My horizontal asymptote will always be those 3 cases. And I'm looking at my case here that the degree of the top is x to the power of 1. And the degree on the bottom is x to the power of 1. That's the highest degree on top and the highest degree on the bottom. Since they're the same, we play the coefficient game, which is listed as case number 2 on the front if you want to go back to the front to look at your cases. That means the coefficient up top is 2. As you see out in front of my parentheses, out in front of that x in our non-simplified one. And the coefficient on my x term in the denominator is 1. 2 divided by 1 comes out to be 2. So that's where my horizontal asymptote dotted line will be to help me guide this graph. The x-intercept is always going to be setting the numerator equal to 0 here, which is exactly what I'm going to do. So I go ahead and have 2 parentheses x plus 2 and set it equal to 0. I divide by 2 on each side to get rid of that 2 in front of my parentheses. And then all I have to do left is subtract 2 to move it over away from x. My final answer here comes out to be -2 for my x. And because it's my x-intercept, my y value is 0. So I plot that point on my graph. For the y-intercept, remember that's always going to be where we replace x in our simplified function. And I'll go ahead and give myself more space by doing it down below. And what do I replace with? X, 0, because remember for my y-intercept, the point will always be at 0, comma, a y value because it's a y-intercept. So f of 0 instead of f of x equals 2 instead of x plus 2, I have 0 plus 2. And then instead of my denominator, x minus 2, I have 0 minus 2. And I solve that down. Inside my parentheses, that's more order of operations per 0 plus 2 is 2, with a 2 outside still. And then in my denominator, I can also simplify down 0 minus 2, which is -2. Multiply the two numbers up top gets me 4. And then I divide 4 by -2 to get me -2. And that's exactly what I'll plot on my graph for my y-intercept. No slant asymptote here again because the degree of the numerator is equal to the degree of the denominator. The slant asymptote only happens when you have the degree of the numerator being 1 degree larger than the denominator, and they were equal in this case, so that was not the situation. For domain and range, remember we always include the x value of our hole in our domain if we had a hole, but we don't. So then I must also always include the vertical asymptote x value of 2. In the range, y can never be equal to the y value of the hole, but no hole in our graph this time. So I just include the horizontal asymptote's y value of 2. Now we need some points in between all of these. So remember, I'll go ahead and start labeling kind of 3 points to the left of my vertical asymptote dotted line and 3 points to the right. So my vertical asymptote dotted line is at 2. I don't know what's happening at 1, so I'll include it in my table. I do know what's happening at 0, but I don't know what's happening at -1, so I'll include that as well. On the right side, I have no idea what's happening at 3, 4, and 5, so I'll go ahead and include those. I'll go ahead and erase those numbers. That was just to get some points in my table. And we'll go ahead and solve these down, plugging these into our simplified function. So instead of 2 parentheses x plus 2, I have 2 parentheses 1 plus 2 over 1 minus 2. And doing that math all together, you should get 6 in the numerator and -1 in the denominator, which comes out to -6. So when I have my x value of 1, I have my y value at -6. For -1, I do the same thing. Everywhere I have x in my simplified function, I replace it with a -1, which is going to come out to be 2 over a -3. So I go at -1 down 2 over -3. It's an estimate. Okay, so with those points now, I can go ahead and connect my points. And remember, at the ends after my points are here and connected, I'm getting so close, but never passing my horizontal and vertical asymptote here to create that kind of boomerang shape. When I plug in 3 into my function, that's the next number I have, I go ahead and get a 10 over 1, which comes out to be 10. So that's going to be kind of off my graph way up here. For 4, I go ahead and plug it as well. So 4 plus 2 inside my parentheses. Instead of my denominator, x minus 2, I get 4 minus 2. And that comes out to be a 12 over 2, which is 6, which I can plot on my graph. So at 4, I have my y value at 6. For 5, last one here, I go ahead and plug into parentheses 5 plus 2 over my 5 minus 2, and that comes out to be a 14 over 3. That's an improper fraction, so you can change it to a decimal, which would be 4.6 repeating. You could also change it to a mixed fraction to see it as 4 and 2/3. So at the x value of 5, I have 4 and 2/3, or 4.666 repeating, and that's going to be about estimated there. We go ahead and connect the points we do have and make sure it's getting so close but not passing our horizontal and vertical asymptotes.